Hello, ELITE Cohort 4. I'm super excited to be back with you for Lab 2, which is multiple regression. We use multiple regression to predict outcomes, or at least that's one of the ways that I'm going to use it today. And so what I have here is I have a data set that I have downloaded from Performance Matters. And what I've included is I've included the 2018-2019 FSA scale score. And then I also included the 2018-2019 Unit Assessment 1, 2018-2019 Unit Assessment 2, and 2018-2019 Unit Assessment 3. So essentially, each of these tests, these unit assessments, were actually given before the FSA this year. And so these are 10th grade English language arts scores. And so what I would like to see is if I can use students' performance on the first 3 unit assessments to predict where they're going to score at the end of the year on the FSA. And so that's my basic purpose for today. We're going to look at the correlation between each of these scores individually, but we're also going to look at the multiple regression and their correlation as a package. So in order to do that, what I need to do is I need to take and make sure that I put this data into SPSS, because in just a moment I'm going to do that. I'm going to right click, I'm going to copy, and then I'm going to put it into SPSS, which I've already done. So as you'll see, I've already changed my variable names. I have FSA, which is one of my variables. That is my criterion variable. I have UA1. Excuse me. I have UA2 as a predictor variable, and I have UA3 as a predictor variable. You're going to want to make sure that your type of variable is set to numeric. Otherwise, you will have issues running the multiple regression. So I'm going to go back to data view, and to run my regression analysis, I'm going to go to analyze. I'm going to go to regression. Once I'm at regression, I'm going to click on linear. When I click on linear, oops, let me reset. I am going to move my dependent or criterion variable, the FSA, into the dependent box. I'm going to move my predictor variables or my independent variables down into my independent box. So I'm using Unit Assessment 1, Unit Assessment 2, Unit Assessment 3 to look for a relationship to the FSA, the scale scores on the FSA. Before I actually run this, I want to go look at my statistics, and I want to make sure that everything's set the way that I want it. So I do want to include descriptive statistics in my output, so I'm going to do that. And then I do want to show confidence intervals because it helps me interpret the data, because it will help me determine from another statistical measure whether or not that there is significance in my correlation. Based off the textbook reading this week, you will have read that correlations are determined based on a 0.01 significance. And so I am going to set this to 99% confidence, which will give us the 0.01. I'm going to click continue, and I'm going to go to plots because I want to do my scatter plot or my scatter graph as it was described in the textbook. And so I'm going to choose my t-dependent variable as my y. And then I would like to make predictions. So I'm going to do z predictions, and I'm going to move that to my x. I am also going to make sure that I have produced partial plots because I like to look at the relationship or the correlation between each of the predictor variables individually or separately. And so that's something that I prefer to see with my plot. I want to look at each one. So I'm going to click continue. I am going to click OK. Please note that the method should say enter. We are not using these other methods. We are going to be using the enter method, which means that the program will be using whatever data we put in it without manipulating it for us. The other options would manipulate the data and remove things based on the data set. But we're just going to do a basic, leave it as enter, please. And then we're going to click OK. And what it has done, it has produced an output for me. And so what you're seeing here is when you look at the output, you're going to see that there's a basic descriptive statistics table. you will see that there's a correlations table. You're going to see that there is a variables entered / removed table. You're going to see that there's a model summary table. You're going to see that there's an ANOVA table or an analysis of variance table. You're going to see a coefficients table, and then you're going to see a residual statistics table. We are not going to be using this table this week and for this lab. You will see the charts that are included as I requested. I have a scatter plot to predict for my multiple regression, my predicted values. And then I also have a graph that shows me the correlation or the relationship between each of the variables. So this is my first predicted variable, UA1, and then my criterion variable, the FSA. And then I have the same thing for UA2, and then I have the same thing for UA3. I like to see those, but it is not required for this lab. I believe you can answer the questions on the lab without it. I do want to show you how to include a line of best fit because it will show you the equation. And so here's what I wanted to do. What I'm going to do is I'm going to double click this chart in the output window. And what it does is it opens up a new window called the chart editor. I can add a line of best fit by looking at this chart or including this chart. So what I have here is I have a little icon that says add fit line at total. I'm going to click that. And when I click that, what it does is it adds a best fit line for my predicted values. And so now this is my regression analysis chart with the line of best fit. And so I'm going to continue to explain the charts and I'm going to continue to explain the output, but I'm going to switch over to a PowerPoint that I've annotated for you. So that way, those of you who are visual can see some annotations while I am presenting the information. So what I have here is I've just taken and I've copy and pasted each of these into the PowerPoint so that way it's larger for you. And I've included a meme here because by the time we do lab 2, we're getting so good with inferential statistics that descriptive statistics, they're just basic for us now. And so basically we have our mean, our standard deviation, and the number of data points that we have for each of our variables. We have our outcome variable, and then we have our 3 predictor variables. That's very basic information now at this point. So now getting into our inferential statistics, we have our correlations table. And so the way that you read the correlations table is it's actually a matrix. And the way that it works is you use the left column to find the meeting point of the top column. And so, for example, if I wanted to compare the correlations of FSA 2018 to FSA 2018, I find that there's a correlation of 1, which is a perfect correlation. Well, there should be a perfect correlation because they're the same exact scores. And so as you'll see, every time one of our variables meets from the top and the side, you're going to get a perfect correlation. So this perfect correlation goes down at a diagonal all the way through this matrix. But in order to read the matrix, we really only need to read the correlation between UA1, UA2, and UA3. So our correlation value, Pearson's R for UA1 is 0.743. And so I know based off table 8.1, page 236, that a 0.73 is greater than 0.5, which means that UA1 has a strong correlation to FSA 2018. I know that it's also a positive correlation. And the reason that I know that it's a positive correlation is because there's no negative number in front of it. Okay. So I also see that Pearson's R is giving me a 0.532, which according to the text is a strong correlation for UA2. And then it's also giving me a strong correlation for 0.588, which is for UA3. So according to this, there are strong correlations to the FSA within the data. And it is greater than 0.5, which again, table 8.1, page 236 says that anything for social science research is greater than 0.5, okay? So our significance for a one-tailed hypothesis is greater than 0.01, or excuse me, our p is less than 0.01 p-value. And so we're going to reject the null hypothesis based off this table. Page 251 says correlation is significant at the 0.01 level. And so this is less than 0.01. So we can reject our null hypothesis. Looking at the model summary table, we have 4 values that are reported to us. We have our regression correlation, which is 0.781. We have our R squared, which is 0.610. We have our adjusted R squared, which is 0.590. And then we have our standard error of the estimate, which is 15.27. So looking at the R, what you're going to see is that we're going to use our correlation coefficient. R is greater than 0.5. So this is a strong correlation. Again, page 236. Then we have our R squared, which is the amount of variability that the model was actually able to calculate and consider and account for within the actual calculation, which was 61%, which isn't bad. That's actually pretty high. So 61%. Then we have our adjusted R squared. And what the adjusted R squared is, it looks at the differences in variance or variability within each of the data sets, and then it basically weights it the same way, or very similar to the same way that a weighted gradebook would be used. Is it readjusts the R squared value based on particular weighting. And so here you'll see it didn't change very much. It changed from 61% to 59%. Then we have our standard error of estimate, and the standard error of estimate is okay. The smaller the standard error of estimate, the more accurate the predictions are. And so we have a 15.27, which is average. We have our ANOVA table, and our ANOVA table is used to determine the F value and the significance of the variance within our sample. And so here, if you look at each of the columns, we have our sum of squares, which tells us the deviation from the mean. It's related to the total variance of all observations. We have our F value, which is, if you look at page 579 or appendix C.6, this is very similar to a t value. It's basically the ANOVA's version of the t value. And if you could look at the chart to determine this number, you would see that there is a statistically significant variance in the sample that I've used. But I didn't bother to look it up because my significance p-value here, it's lower than 0.0. I'm sorry, that's a typo. It should say 0.01. It is lower than 0.01. So we are going to, again, stick with the fact that there is significant variance in my sample. We have variables entered and removed. And so based on the model, we chose the enter method. If we had chosen another method, it may have removed variables based on the amount of variance. But because we choose the enter method, it read the data as I put it in. And so it did not remove any of the variables. It kept all 3 variables in the model. And then we have our coefficients table. When we look at our coefficients table, it provides us with our y-intercept and our slope for the equation. So if we're here, the constant is always the y-intercept, and then the decimal point here is UA 1.714. That would be our actual our slope for if we were comparing UA 1 to our to our FSA score. Same thing here, UA2, UA3, that's our slope and our y-intercept. So then we go on to predicted scores. So this is my best fit line if I were looking to make predicted values or predicted versions. You'll see that my equation for my predictions are there for my regression. And then I also included my 3 graphs for UA1, UA2, and UA3, you'll see, and then you'll see for UA1, you can see a strong positive correlation. There is a strong line of best fit there, but you'll see that the line of best fit shows a weaker correlation for UA2.